Hello, more work on exponentials today. This is where we are not quite sure what the exponential equation might be, and we're trying to find the equation from real data, and we're trying to use our knowledge of exponential graphs to find the potential equations that might be lurking underneath the data. So let's have a look at it. On the starter then, we're going to draw, I think, a graph. It says in an experiment we get this information of the temperature, which is measured or recorded as theta, which is quite often actually the case that you use this Greek letter for temperature. Often it's an angle as well, but for temperature we use it against time. So it's a temperature against time graph. Now what is it? It's measured in different times, so it looks like it's being warmed up, and it's how quickly the temperature of this thing. Either it's warming up because of its reaction or whatever. It's being warmed up because it's got Bunsen burner underneath it. But basically we get we wants us to draw a graph of the temperature against time and then work out the relationship. So let's have a go at this. Now first of all, my t values go from 20 to 120. So I'm just thinking to myself, what should I do? I'm going to draw that as 0. 20, 40, 60, 80 clearly isn't enough. So why don't I just make life easy for myself? 50, 100, 150. It's not quite like science, this. I wish I could draw a better straight line than that, but you get the idea. And going up, I have to go from 16.3 up to 36. Tempted to still go 0 to 10. Yeah, let's do that. 10, 20, 30, 40. Now this is theta going up. These are the temperatures. For my dodgy axis on this dodgy tablet. That's not bad. I'm quite pleased with myself. And this is time. So let's plot my points. It says 20. Now each one of these two squares is 10. So I'll just bear that in mind. Going up much easier. So 10. I've got to go to 20, which is obviously there, and 16.3. That's 16, so 16.3 is about there. I always put crosses. I want you to draw one of these as well, please, as I'm doing it. 40 and 20.4. So 40 and 20.4 is about there. 60 and 24.2. 60 is there. 24.2 is about there-ish. Now from dodgy lines. 80 and 28.5. Now 80, and what did it say? 28.5 or 28? 29. So the 0.5 is in between the two. That's it. 100 and a 32. So that's easy to do. And then 120. It's about there. And that is at 36.3. So now for me possibly plotting them. They look in a straight line. Of course, that's the point of doing this. We want them to be in a straight line. Now, I've just tried it badly, but that's the best I can do with my dodgy tablet here, to draw a straight line through the points. And of course, you just draw a straight line. Now, the critical things is that I can, even with my dodgy straight line, work out this y-intercept point, and that looks to be, to me, as if it's at 12. And the other thing I need to know is the gradient. So I'm just going to do as best I can. That goes across, that goes down. You draw yourself a little triangle. That goes 50 across. You have to use the scale, 50 across, 0 to 50. And going up, it goes from 12 up to, I'm going to say, up to 22. So that goes 10 up in that space. And then you find the gradient, of course. You do the up divided by the across. And if I do that, I get 0.2. So this gives me a relationship. Normally it's y equals mx plus c. But in this case, my y-axis is theta. My t is my x-axis. And my m, it says, is 0.2. So I'm going to write 0.2t plus 12. Now I've done this in the past. Let's see what I've got in the past. Well, that's quite close, actually. So allowing for last time, whenever I did it, I seem to have got a better answer, 12.3. That's what we do. We go through and we try to work out the gradient and the y-intercept, and then you can write your equation. So that's basically what we're doing, apart from now we're looking at curved data. And it says here that if we have curved data, we try our best to think of a curve which will go, that it kind of approximates. As long as it's straight, you see, you can get a line of best fit, and that's no problem. But if it's curved, for instance, if it's a polynomial, this is a polynomial, y equals ax to the b. You can see it's polynomial because that might be, for instance, y equals 3x cubed or to the 6 or something like this. You know, I don't know what b is or a is. It could be a horrible number like 6.29. But you can see I'm effectively saying y equals x equals y equals some function of x where x is to a power. The alternative is we have an exponential function. And when it's an exponential function, it might be, for instance, very similar, but here it's y equals 3.24 to the power of x. And you can see it's a subtle difference between the two types of equations. One, the power is the x, one, the power is a number. Both cases, we need to find the magic numbers, if you like, for these equations. So suppose we have this type. This is a polynomial. You know it's a polynomial again because the power is just a number. N is meant to be a number. So this is basically the argument. Y equals ax to the n. We take logs of both sides. So therefore I get log y equals log ax to the n. You're meant to be able to do this in the exam, so definitely make notes on this. Now, because it's a times in the middle of that, it means I can split it. I can write that as log a plus log x to the n. And because we've learnt the log rule, where not only can we split it and it becomes a plus, we also know the power law brings that n down. So this becomes log a plus n log x. Notice that's log y. And that's what we've got here. It said show that that is true. Explain its significance. Well, we basically line this up as y equals mx plus c. Oh, the slight differences, I suppose. Here, I think this is my something x. You can see it says log x. So I'm going to think this is like my mx plus c. I've written it in a different order. But what that tells me is that my y-intercept that I get, my y-intercept is equal to log a, and my gradient is equal to n. And it allows me this effectively to find the missing things, the a and the n. Let's do a question like this. It's an example then. It's believed that some relationship exists between x and y on the form y equals ax to the n. Draw a suitable straight line graph to confirm this and estimate the values of a and n. Well, first of all, let's go back to this y equals ax to the n. If this is true, let's work out what graph I need to draw. You'll recognize this. It's the same thing we were just doing just now. Log a x to the n. And I can split that. I get log a plus log of x to the n, which is log a plus n log x. Notice these logarithms are the natural logarithm. And again, this is equal to log y. So therefore my y equals, again, that's my m, that's my x. Notice I just write capitals at this point. So I'm expecting to draw then a graph. Normally you draw a graph of y and x. So what this tells me is I'm going to draw a graph of log y here, not y, because it says y is log y. And if I draw a graph of these, I'm not going to draw x on this axis, I'm going to draw log x. This is the weird thing that we have to do. So this is my information that I've got. The very first thing I need to do is because it says here, we need to draw log y and log x on our axes. That means I better find them. So I need to draw a table. I need to get a table that says log x and log y. And I'm going to type these into my calculator, and I'll write them down, and I'll come back to it. I've deliberately written them all out, but I've left the last two. So to get this last one, just to show you what I'm doing the log of 8.1. If I type in the log of 8.1 now, I get 2.09. And the log of 69, for the one underneath it, I get 4.23. Again, I do the same thing as last time, but I've said to you I need to draw log y on this axis and log x along this way, and I think this way I will get a straight line. That's the plan anyway. So I need on the log x, I need to go across to 2, so that's pretty easy. I don't necessarily need to use my whole of my graph paper, so I won't bother. So 0, 1, 2, 3, and this is log of x going across. What do I have to do? I have to get to 4. 0, 1, 2, 3, 4. Let's go a bit higher because it goes to 4.23. Now what I would say is some people want to use really complicated axes. Don't. Pick a really easy scale. You're the one who's going to have to use it. So I'm going to plot my points. So as you can see, what I've done is I've effectively managed to draw a number of points, and they look broadly in a straight line, allowing for the fact that, again, I'm not 100% convinced that my points are perfectly plotted on this dodgy tablet. Now what I need to do is draw a line best fit through them, so I'll do that now. Now I've drawn one. I don't think it's perfect by any means. I think it's a little bit low, but on this tablet it's rather tricky to do. But nevertheless, what I'm going to do is I'm still going to pretend it's accurate. So taking that off there, I reckon that looks like a I'm going to say 0.75. I don't know exactly what it should be. And up here I need to find the gradient. So I can pick any point I want. So might as well pick that one there. As good as any other. And I'm going to go 1 across. I don't have to go 1 across. So that looks really handy. See, that looks like a easy one to do. So that goes 1 across. And I reckon it goes 1.6 down. Now the gradient then is 1.6 divided by 1, which is obviously 1.6, and my y-intercept is there. Now remember what I said. I said that the log y and the log x when I plotted it, this would give me these, and this is how it helps me. I know my c, my y-intercept is log a, so my c, which is 0.75, is equal to log a. Now bear that in mind, because I can now move the log onto the other side, and I get e to the 0.75 equals a. And I don't know what e to the 0.75 is. I'm going to type it in now. E to the 0.75. 2.12. I reckon a equals 2.12. If that's right, I'll be amazed. By right, but I mean accurate to how I did it last time when I did a proper piece of paper. And the other thing I said last time was I said that the n and the m are equal. So that therefore the gradient is equal to n. What was my gradient? It was 1.6. So this then tells me my equation y is equal to a, 2.12, times by x to the power of 1.6. That's what I think it is. That's what I said last time. I said 2.0 to the x to the 1.8. So you can see last time I got a slightly different equation, but it's close. It's close. I quite like that. It's close enough. You don't have to be perfect here. Obviously, the more accurately you do it, the better it will be. So we're trying to get approximate answers and get some marks. Now, there's a second model, which I can show you the math behind it. I'll do the example of it in class. Now, this is the exponential model. It says kb to the x. So I do the same trick. I take logs of both sides. Log k b to the x. I did the same thing last time, and I then split it because it was a times. Equals log of k plus log of b to the x. And I can then bring the power down to the front. But you'll notice because the x is the power, it just changes things. The reason why it changes things is when I write my y equals, my m is here because this is my x plus c. And what it also means is when I draw this graph for this y equals mx plus c, where it crosses the c, the y-intercept will be log k. And my gradient now is, that's a log as well. So my gradient, my m, is log b. And this will allow me to find the k and the b in an equation. Now in class then we'll have a go at this example. It is believed that following data follows this formula. And that's an exponential formula. There's the data. Oh, horrible numbers. Horrible numbers. Definitely going to do that in class. There's a good thing for us to do now is stop and we'll carry this on next time. Okay, bye.